In this video, we're going to go ahead and take a look at slope fields again. A little more about what do they really mean. So we know that each of these little segments represent slopes. Now the thing is, we have something called a general solution to a differential equation, because in order to solve a differential equation, we have to integrate, which causes that issue of the constant of integration. Remember how when we would integrate, we ended up with the answer, and then we have to put plus c at the end, and we don't know what c is. So we need some sort of initial condition, some sort of point from the original function that will tell us where to go. For example, if we have a point here, then we'll just follow along from that point on. And that's what we see in all these different colors, is based upon an initial condition, we end up with these different answers here. So given the initial condition 0, 2, so 0 when x is 0, that's right here on the y-axis, and 2 is a point right here, we're going to figure out what's the range of the solution. Now notice this is a horizontal, these are horizontal slope fields, or whatever they're called, the little segments on the slope. So if we follow this along to the right, you'll notice that it'll have a horizontal asymptote right there, because it's not going to break past that horizontal slope if it continues to stay horizontal. Same thing to the left. So we actually have a restricted range from 1 to 3. So these different questions, they're going to vary. This time it's asking about the range. So that's the set of y values, and that's going to be contained between 1 and 3. I'm not sure if it actually equals 1. I would have to look and see what Kant says. So for now, we'll leave it open. And actually, I just read the question. This is saying for x greater than 0. So what that means is to the right of the y-axis, so from here on. So actually, it starts at 2, and it does equal 2. And then it drops to 1. So really, our range is from 1 to 2. I'm going to leave it open at 1 because I'm not entirely sure. I don't think it actually may ever equal 1. It might just get really close to it. And that's what our range would be. And they might put like an interval notation on it. Who knows? What is the general solution to this differential equation? So if we look at these functions, which one of these functions looks like the solution? So if I were to just a picture, let's just put a random point. Let's place it here, and then we're just going to follow along, and then you'll notice, oh, okay, so our solution, that looks like a parabola, doesn't it? So the parabola has the shape of y equals x squared. So, you know, you could always graph each of these in Desmos and see which one is kind of looking like that. X equals y squared. So let's go through each shape real quick. So this one I know is going to be a parabola. This one's actually going to be a sideways parabola. We can see that in Desmos. So if your slope field was causing a sideways parabola, that's what you would answer with. So that's your sideways parabola. Y squared equals x squared. I don't know exactly. I think that might be a V-shaped graph. Let me just see real quick. Y squared equals x squared. Yeah, kind of like a V-shaped graph, right? And two V's there. It's like an X-shaped graph, so that's kind of crazy. And then you also have, this is the classic circle equation there. So just depending upon the way the solution looks, here you can see that parabola shape to it. Or if you were to see a sideways parabola or an X shape, or, you know, if it's a circle, I mean, so you can tell pretty quickly what equation, our general solution. No, it's called general because we're missing that constant c. And I think later on we're going to find the particular solution and talk a little bit more about how we go from the general to the particular.